So this is our topic 1, cycle 1 learn lesson, following up the Motion Man PhET simulation that we did today in class. So let's talk about a couple of definitions that we were investigating. Speed. Speed is a distance over time. As we see distance, we'd represent with d, measured in meters, and time in t, measured in seconds. We can also represent that distance as a change in position. So distance is how far you went. When he went from 0 to 10 meters, the change in position would be 10 minus 0, or 10 meters. The change in time was, if he's going 2 meters per second, 5 seconds. And that'd be 5 seconds minus 0 seconds. So just the change in time in our denominator and the change in position in the numerator. So that delta, the triangle, means change. Speed is distance divided by time. Speed and velocity, here's the difference. When our Motion Man was moving right and at 2 meters per second and left at 2 meters per second, his speed is the same in both of those cases. However, his velocity is opposite. And moving left, we consider that velocity to be negative. So velocity takes into account direction. So it's a vector. And we'll learn about different quantities in physics that are considered vectors where direction matters. So it's the amount or magnitude and also the direction, both effects. Let's look at some common units. So we've gone over these, but meters for distance, and there's our prefixes. Kilometer and meter are going to be the most commonly used, although there's the centa, which is 1/100th of a meter, and millimeter, which is 1/1000th. Time will generally use seconds, but milliseconds, minutes, hours, days. Those are other ways to measure it. Speed and velocity will usually measure in meters per second. You'll sometimes see that as kilometers per hour. So speed is distance over time, where that position is measured in meters and time in seconds. So let's look at a problem for this, what it might look like. We're looking for, so here we go, calculate the missing quantity, v, d, or t, for the object in bold. A car moves 3,000 meters in 30 seconds with constant acceleration from rest. We're going to look at constant acceleration, meaning no change in motion to start. And then in our next unit, we'll go on to what happens when we have acceleration. So here is the way we're going to be solving problems. We're looking for, well, it says we're looking for velocity because we're given the distance, d, is 3,000 meters, and the time is 30 seconds. So the relationship we're going to use here is velocity equals change in the distance over time, delta x over delta t, or the distance it went, d over t. So here we went from 0 meters to 3,000, so the change there was 3,000 in 30 seconds. So 3,000 divided by 30 is 100 meters per second. Now remember that if you were just to write 100 for this, it wouldn't be accurate. We need to know if we're talking about kilometers per hour, lemons, whatever it may be, computers. We need units to make our answers make sense, and also for us to do a reality check at the end. Does that seem to make sense with the values I was given? Yeah, that looks reasonable. Maybe I flipped it 30 over 3,000 and I'd be like, oh, that's really slow. When I look back at it, that value doesn't look right. So again, that's how we're going to do a basic problem calculating velocity. The problem I'm going to have you solve now is a jogger jogs at 10 meters per second for 2 minutes. How far did she jog? We're looking for distance. Try pausing now and working on that one. Okay, we're looking for distance. We're given that the velocity is 10 meters per second. The time is 2 minutes. So we could use our relationship that if we rearrange my formula v equals d over t, I can see that I can solve for the distance, or I could just plug in values and then solve algebraically. So 2 minutes, we want to convert that to seconds. Remember when we do a conversion, what you want on top, what you got on bottom. Sing it again. What you want on top, what you got on bottom. I want seconds, I have minutes. So I multiply this by the conversion factor, which is 60 seconds per minute. Then the minutes here, minutes over minutes cancel, and I'm left with 2 times 60 is 120, and then I'm just left with seconds. The one thing I should note here is I'm going to be more exact with my 2 minutes, with my sig fig rules, to make sure that that all lines up to use 2 significant figures here. So when I solve, I can see that 10 times 120 is 1,200 meters. And that's how far she goes. Okay, you're going to have a problem pop up on the screen now where you're going to be solving for velocity, distance, or time, and then go ahead back to the video. Okay, so we looked at calculations for velocity. Now we're going to look at what graphing it looks like. So here we have the data for similar to the Motion Man, but this is a little buggy that I measured the displacement, the distance it went, its position over time. So we can see that I put my explanatory variable, time, on the x-axis. You may have also heard that called the independent variable. Explanatory variable is a better way to describe what we're talking about there. And the response variable is position. You may have heard that on the y-axis called the dependent variable in past classes. We're going to refer to these as explanatory, and you can always remember explanatory x. It's explaining the change as time goes because of the velocity, the position changes. And that's the response variable. It's responding to the explanatory variable here. So here we had a buggy at 0 seconds that was at 100 meters. After 5 seconds, it was at 120 meters. So I can use any two of these spots to calculate its speed. And in fact, the slope here is the change in y, so 120 minus 100, which is the change in position or distance, 20 meters, over the change in my x value, which is 5 seconds, or the change in time. So the slope of this graph is my speed. So I can see that this slope at 20 over 5, it goes up 20 over 5, 4 meters per second is my speed. Now I can look at it here, and because the difference here is that we have the same difference, it goes up 20 over 5, it's still 4 meters per second. So another way, I could keep calculating like that, but I know that this is a straight line, and that straight line of the slope tells me that it's a constant speed. So all throughout this data, it's 4 meters per second. I could use any 2 points on this graph to calculate that. And that key on my position versus time graph, that straight line indicates constant velocity. So that's something to know, how to calculate velocity from the graph, and then also how to interpret it based on the shape of the graph. So time will always be on the x-axis as explanatory, position on the y as response. You have to have an evenly spaced graph so that it's unbiased. We label with units, with the variable and units. And sometimes intersecting graphs, if I wanted to put 2 buggies on here, like let's say I was driving 2 cars, I could see when they intersected. So when graphs intersect, that's when, that means their time and position is the same. That would be when they would like collide if they were going on the same line, or they'd be at the same position. So that's the key with graphing. Now think about what this would look like if my buggy was moving the other way. So if it started it, let's say it started up here at 180 then, and I send it back, I turn it around. So it's going to have a negative velocity. And instead, this point here would be up here, and we'd have a downhill from left to right shape, where this point would be over here. So a negative slope indicates a negative velocity, a positive slope, a positive velocity. And those are really our key takeaways here. So position versus time graphs. And we're going to look at just this column right now. On a position versus time graph, no motion would be a slope of 0. That's a horizontal line. Constant velocity would be a slope greater than 0 and unchanging, meaning the slope's not changing. And a constant velocity going the other direction would be a slope less than 0 and unchanging. If I had a curve of some sort or something that's not a line, then it's showing that there's not constant velocity. We're going to get into that, though, in our next cycle. So you're going to have some questions now about interpreting graphs to complete, and then feel free to email any questions you may have.